Yeah.
Usually my classes are like 4 or 5. That's why I started doing 3. So then I struggle with like.
The parking's so bad this year.
I think my 5.
My friend was joining me and we like getting food. We're there 20 minutes. Just trying to think of something.
I know.
Keep going, keep going. I'm like, oh, I took shit. And I was
I really waited for something to leave and I was like,
yeah, generally, it's kind of creepy. You just gotta follow someone while they're like walking to their car.
exactly.
Want to shake your hand?
You caress it
Say no.
like that.
I got it. Hey. One time. Last time. Last time. Why not?
My girl wouldn't allow me to hold anyone else.
I'm not attracted to men, it's fine.
You're weird for that.
What do you want me to say? I'm attracted to men?
Huh?
You want me to say I'm attracted to men? Make you feel better.
Yeah,
Okay.
he gets it. Say you're attracted to them. And I'll take it.
No.
This your time.
Yeah, I miss you.
What?
Yeah, but I like the summer I was maybe. It was like a 2 hour to be. It was so bad. I can't believe they question. I'm not getting that. This weekend. It's literally literally go to now. I'll snowboard. Yeah, I can't pass. Oh, my friend, I can't pass. Okay. Then I got to scout and to scout and to come on. It's still like compared to the one phone. It's so bad.
What's up? Hanging in there. Getting through it. How are you?
Good. I kind of wanted to ask you questions with answers because I'm
Okay.
and child like
Yeah. No, so ANSYS is more, well, we do it more for kind of structural modeling. I'm thinking probably your case is probably looking for the relationship between like the engines, the rotor's output and utility. Yeah, so ANSYS is more for like structural thermal modeling. Not so much for that.
so we need to be more it's gonna be on the chassis.
Exactly, yeah, so design of the chassis itself and kind of the structure for that. You can use finite elements probably for that eventually. But it would be a really complex one, so we're mostly just the kind of basic structural, basic stuff.
Yeah, because the top
Yeah.
they were using.
Oh, okay.
I was just like confused. That's why it's
Oh, okay, I mean, yeah, I mean, there's probably a way you can do it, but yeah, not it's not anything we're being custom.
because
Yep. Hey, what's up?
So I'm taking a computer right now.
Okay.
Okay. I'm trying to switch over to a different G.
Okay.
So I need to be on the wait list for that. All of my wait lists available.
No, what's my name?
Class.
Yeah.
I'm the one for it.
I see, I see,
Do I drop?
What's my name? What's my name?
Class.
I see, I see.
Just like what my chances are. For example,
Yeah, I mean, so right now,
I don't care.
we have a lot of constraints because we have an accreditation coming up.
What?
So basically, outside people are gonna come assess our
We're
program,
not gonna. send
and so we need to make sure that all of our electives are balanced in terms of enrollment. And so this class optimization, both very popular, but then, the more of you guys have those classes, the less you are. And so, right now, the messaging from the department is that I'm not gonna accept anyone from the wait list until all the other courses are filled up. But I know it's not as simple as that because it's, people have scheduling conflicts and, these electives, you just.
Oh, you have 401 too?
A lot of people have interest in like optimization analysis. And so I think what I've been trying to do is I think probably.
You have a fun time.
Yeah, he just read.
Classes, so if you're top five, I'd say you're pretty safe.
About how
Stick
we
with
could be
it,
better.
like, for kind of 7, 8.
So someone asked him to bring the coffee then.
Probably maybe look for.
Probably schedule
Just make sure to.
Okay.
Okay.
Oh.
And it's an easy.
Yeah, we'll try to avoid that as much as possible. That's the challenge, I think, that, with this kind of inflexible policies. So, we want to. Yeah, let's talk next.
Thank you.
Yeah.
I'll schedule something right now.
Okay, sounds good.
Will I be seeing more of you? Will I be seeing more of you? Hopefully.
Bring my stuff up here.
Why are you so flustered all the time?
It's like the Snyder Cut when I.
Okay, when did you guys try opening up Ansys and see if it works for you guys? It's so if you search up on the start menu, you want Ansys Workbench 2024. If you search up Workbench, it should be that. But if Ansys doesn't work today, you're kind of bummed because.
Also flustered?
Yeah,
I have like a lot of answers tabs, but it doesn't say the word.
Oh, it's not
Just
just.
you just search Workbench.
Oh, there it is.
Yeah.
There you go.
I have nightmares. We do Ansys and it doesn't work. Our IT is very reliable. This never happened.
I'm so tired.
It looks like the license server has.
I just finished that. I just finished saying
That time of year,
school thing.
where like they have to renew everything.
They should have renewed it. I mean, the fact that we have the newest version, because we didn't have this last year.
They have.
Usually that the renewal happens.
So in the pocket, bro, on board. I'll run them with you.
If Andrew doesn't work,
Thank
we
you.
may push the activity in there.
Imagine running some pocket.
Yeah.
When you get it back.
There's an issue, so what happens is that you pay for all the licenses and it's stored on a server.
It's like, bro, by yourself.
So I think there might be an issue with that server or. Okay. All right, we may have to hit it.
Day one.
Oh, and since you dropped
Time doing that by then.
early job here. He was waiting at the one of those when that Chinese ship came in. I was like, you were on vacation. It's released.
I noticed that there was a spot for my signature, but I'm like, maybe we're gonna sign it after we talk on Friday.
Yeah. It's up to you. It's mostly just for the ASA.
Oh, yeah, I mean.
We're not gonna like sweet.
Gotcha.
It would be just an underneath done the training.
Okay, yeah, I'll sign it, when I get back.
No, just take your time. I'm running all this.
Gotcha.
Just basically.
Yeah.
I want to add. My knowledge sees the students going, it's also a student thing. Oh.
Gotcha.
Did they just download school?
Imagine that she just. Think of the
Okay.
Yeah. Right? Just how many saw.
Yeah. Okay.
What's in.
Yeah. Okay, sounds good.
So it's that, it's mostly these hundreds.
That's it, I'm trying to read.
Okay, I'll sign one again.
There's a reason why he's the one.
That's crazy.
Well, I don't
Yeah.
What's up?
Yeah.
Oh, you're the
We're still kind of struggling.
I'm just like, I'm on the team, so it's like.
Okay.
Kind of designing right now, so much. Yeah, he starts manufacturing, I'll see.
You'll be like.
Right now needs more cheap.
Okay, well, at least now I know. Well, you're a normal color, right?
Yeah, I was chilling there all day, your food, your 3 lunches.
They eat my pasta, then eat my meat.
Yeah.
Workbench is a one up.
I might pull.
It's like they're.
I might just pull. What did I say? I didn't say anything. Are you focused?
That's crazy.
I didn't say anything.
Yeah, what part is that?
That's what you said about. You said that about Vietnamese people. You said that about Vietnamese people. I didn't think you.
I don't have it.
Most wild.
Let's download
This is
it.
anything about
It's
so I can call it. That's all that went through my head. It wasn't like the whole like thing you said. I'm just like, damn, you can really call him out.
Yeah.
Dude, he was like going about how I was like a jungle book.
See, you can't just.
No,
It's just
you
invalid.
can't, like, that's what you can't just lie.
Yeah.
Yeah.
Hi, Angie. You want to argue? Take care. I'm gonna be back to 7 minutes.
Right there.
Yeah, I'll be right here. I'll keep my eye on it.
It's still.
It's still loading.
Yeah.
I noticed how long it's taking on yours. That's why I'm gonna start it.
Yeah.
Mine crashed.
Or just crashed. No.
It
Hey,
won't.
Alan, what are you
This is
saying?
why we should update to Windows 11.
Yeah.
Dude, it is you. Oh my God. What are you doing here?
Good.
Yeah.
Lost my.
Yeah. Really?
I just wanted to.
Oh, no.
I'm gonna check.
What are you talking about?
I'm sorry.
Hour and a half drive.
I know, I came here straight from work too.
Where is
Why are you
the?
talking
Hey, they should have gone to.
why are you talking about Lake?
Guess we're going to Biggs. Professor, you're loaded.
I thought ICC have meetings.
Yeah.
Did it say?
Yeah, that's. They said.
Yeah, so.
Now, and you go back to the. I'm not.
It should be somewhere in there.
I just don't want to.
Alright.
No,
I'm.
Got that.
No.
I had nightmares now.
Isn't it?
It's finally out today, yeah. In the 6th year. What are we doing today? We're gonna do a lecture. I'm gonna shotgun something. I have the lecture notes on my phone.
714-898.
All right, guys, it's 5:30. Let's go and get started. Bad news. So I'm a bad news first kind of guy. So bad news. It looks like ANSYS is not working on the computers here today. So we'll do our ANSYS activity on Tuesday. I need to get in touch with IT to kind of figure out. It looks like it's having trouble connecting to the license server. So I don't know if something happened to it or if it's overloaded or something right now, but ANSYS is not able to be open today. So we will do it on Tuesday. So instead today we're gonna pivot. So we're gonna do, we're gonna swap places. So the lecture that I planned for Tuesday, I'm gonna do today, and then ANSYS activity we're gonna do next week. Okay. So I'm sorry. I know probably some of you drove here in traffic, hoping to do ANSYS. I apologize for that. You know, I know traffic's really hard, parking sucks, but come back Tuesday. We'll do the answers then, hopefully. Yeah. Okay, so some announcements. So the first homework assignment, so for the very first homework, which is the email. I think a lot of people have already sent me emails, you know, so, you know, just make sure you do that before Sunday. Waitlist people, I'm sorry, I don't have an answer for you guys just yet. But just remember that, you know, we do have a lot of constraints this semester, so I don't think I can accept everyone from the wait list. Most likely, it's probably gonna be around 5 people from the wait list, so if you're top 5, then you're pretty good. If not, then, you know, I would probably look for some other options. All right. Again, you know, today we're kind of pivoting a little bit just because ANSYS isn't working. That's kind of the downside of kind of working with technology. So we're going to talk a little bit about kind of the theory behind FEA and a little bit of that background information. So this was the lecture that I had originally planned for Tuesday. But you know, since this ANSYS isn't happening today, we'll do our ANSYS activity on Tuesday, and I will do this one today. Okay. All right. Any questions on this? Yeah.
I'm not sure if it's like up or not. It's kind of just showing nothing.
Yeah, so on the left hand side, you see stuff like static structural, things like that.
On common system on ACT.
Yeah, that's so ANSYS, there's a lot of free features that they kind of give out for free. But to access the features that we need to, we need the license for it. And it looks like it's struggling to connect with the license. Yeah, so if you try to open up ANSYS right now from the classroom, the program to launch is called ANSYS Workbench. Maybe you can launch it in the background just to see. Maybe the license server will suddenly come online throughout the class. But it's probably going to be stuck. The launch is going to be stuck on checking licenses for probably about 5 minutes. And then when it finally does launch, you'll get an error that says, you know, it can't connect to the license server. Yeah, it's a bit unfortunate, but hopefully, you know, I'm going to talk to IT, you know, tomorrow. Hopefully we can get it fixed before. Okay. All right, any other questions before we get started for today? Okay, all right, so let's go ahead and get started. Usually I have the notes in front of me, but obviously I was not prepared for this, so I'm gonna do it off my phone. Okay, so you know, 410 has this class has kind of gone through a lot of evolution. You know, ever since I first started teaching this back in spring 2019. So my background, you know, in FEA is I've really only learned FEA at the graduate level. And when you learn FEA at the graduate level, we focus mostly on the theory. Okay. Since then, you know, this class has changed a lot. You know, I've learned a lot more about ANSYS, and so we're focusing. You know, this class is almost primarily on ANSYS stuff. But even then, you know, it's still, you know, even in an applications-based class like this, it's still really useful to learn a lot of the theory. And so today we're going to talk a little bit about kind of the background, the historical development of FEA. Kind of where it kind of fits into kind of the scheme of designs of engineering design, and you know how software like ANSYS kind of came to be. Okay, so if you recall from what we talked about on Tuesday, you know FEA is really just a way to solve differential equations on a computer. So, you know, if you take a course that's kind of more in depth on the theory of finite elements, you know, you're going to be talking about differential equations a lot. Okay, and the reason we're so interested in differential equations is well, first of all, you know, let's define a differential equation. A differential equation is some kind of equation that relates the derivatives of certain quantities. And so it turns out that, based on the development of kind of science and math, throughout history, a lot of physical phenomenons, their most kind of reliable models are differential equations. So we talked about a few examples on Tuesday, so things like the fluid mechanics equations, the heat equation, okay? Things like that. Okay. Okay. And so the reason finite elements is able to do this is that it's able to take a differential equation, which is normally a very difficult type of equation to solve, and it turns that differential equation into an algebraic problem. Which, by itself, you say that it doesn't seem like that much of an improvement, right? You're taking one really hard math problem and turning it into another really hard math problem, right? So it kind of just seems like, we're just doing things for fun, right? But the thing with algebra and algebraic problems is that computers are actually really good at solving algebraic problems. And so it's fascinating actually. So if you look at the kind of the historical development of FEA, finite elements was actually developed long before the age of computers, right? It was developed by mathematicians as a way to take differential equations and then put it in algebraic form. Okay. When it was first kind of proposed, people almost scoffed at it. It's like, like this isn't helpful. Like you turned one math problem into another, like big whoop, right? It wasn't really until computers started getting developed and computers started showing that they were actually really good at solving these algebraic problems that, finite elements started to gain traction from there, right? And then kind of one thing led to another, and then, programming became a big thing, and then, development of finite element codes became a thing. And then, now we have all these big companies like ANSYS selling their finite element software to people. Okay. Okay. And so, because of this development, finite elements has become kind of a really big part, a really important part of just engineering analysis and engineering design in general. And so, the way that we obtain or the way that we kind of obtain finite element results, from a physical system kind of follows a particular kind of flow chart. Okay? Or it follows a particular model. So usually, when we are working with engineering, we're going to start with some physical engineering system. Whether this be like, a car, or a building, usually it's something that you're in charge of designing as an engineer. Okay. This physical engineering system has its own governing equations, and so the governing equations are going to be the differential equations that are used to model its behavior. And so at this point, if you were really good at differential equations, or maybe you were working with a very simplified system, you could solve these differential equations outright. Okay. Most of the time, we're not really working in those situations. We have either a complicated geometry or complicated boundary conditions, some kind of complexity. And so we have to kind of work with this. Okay. And so, from here, this is where FEA takes place. And so through FEA, those governing differential equations are often transformed into an algebraic system of equations. And so a system of algebraic equations, these are usually linear equations. An equation of, I think probably what you're probably most familiar with solving is, maybe 5 equations, 5 unknowns, right? That's something you can typically solve by hand. When you perform FEA and you find these system of equations, they're usually much more massive than you typically are accustomed to. And so these are things, these systems could be anywhere between I don't know, maybe like 100,000 equations, 100,000 unknowns, maybe millions, millions of equations, millions of unknowns. So, even though I'm saying that it's a system of algebraic equations, it's beyond the scope of what you can solve by hand. Unless, you had a ton of time on your hands or something like that. Okay? And so the only real way to solve this very large system of equations is to use a computer. And so through this computer, we have the solution to the system of equations. Which, through our FEA is also the solution to our governing differential equations. Usually at this point, the solutions are in some kind of raw form, some kind of vector form that's not really, it's not really interpretable by humans at this point. So there's some degree of post-processing that has to occur to make sure that you can display the variables cleanly. And so this next part is post-processing. Which again is handled in the computer. So it's usually handled by the software. So ANSYS does this automatically for you. And so from here, you usually obtain what I usually call the engineering results of interest. And then usually based on those engineering results, you can use those as part of your design. Okay? And that's ultimately the goal of FEA, or at least modern FEA, right? So in modern FEA, you know, for you guys are kind of, you know, typically kind of users of the FEA software. This is usually kind of the flow chart or the logic that you're going to follow. Okay. Granted, a lot of these things are handled by the software now. You know, finite element software has advanced a lot over the last, you know, 10, 15 years. So ANSYS kind of handles this all on the back end without you really kind of noticing anything. But this is kind of just a peek of kind of what's going on behind the curtain. Okay. From your perspective, you know, as a user, ANSYS, and of course, this would have a lot more context if we could use ANSYS today. But you know, you're just inputting a part, you're inputting the boundary conditions, and you're getting the results from there. But you know, there's kind of a lot of math and a lot of kind of processing that takes place behind the scenes. This kind of gives you a little bit of a preview of kind of what that process actually is. Okay. Okay. Any questions on this so far? Okay. All right, so you know, for this class, you know, we're mostly going to be focusing on structures, and so we're going to be doing structural analysis, stress analysis, applying forces, pressures, solving things for things like deformations and things like that. But just know that any phenomenon that's governed by a differential equation, you can use FEA to solve that. So that includes thermal simulations, fluid simulations. Those are probably the three most common structures: thermals and fluids. You know, electromagnetism to a certain degree too. But you know, anything that's governed by differential equations, you can solve with. Okay. Okay. So the next thing I want to go over is the concept of what I call a boundary value problem. So boundary value problem is not something that's unique to FEA, but it's oftentimes a really good starting point for an FEA analysis. Okay, because everything that you have to define for a boundary value problem are things that you have to define for a finite element problem as well. Okay, so there's a lot of overlap between them. And so if you start to think about your engineering analysis and engineering design as boundary value problems, it helps to kind of get you in the right mindset of, you know, how to set this up properly as an FEA simulation. And so it's a good starting point for any FEA simulation. It's also the great starting point for any analysis. Okay? So any kind of situation where you want to find out kind of more information about it or predict its behavior, basically which is the goal of most engineering analysis. You're going to form a boundary value problem to some. Okay, so there are three main components to a boundary value problem. So part one, or we'll call part A, is the domain. So the domain, kind of in kind of more plain speak, represents the geometry of your analysis, and so it's the what you're analyzing. in kind of more formal terms, it defines the boundaries or defines where and to what extent we want to solve our governing equations. So that's the first thing you have to define with the boundary value problem. It's also the first thing we define for an FEA simulation, finite element, okay? Again, this would be great if we could do our ANSYS activity. But almost the first thing that you do when you run an ANSYS simulation is that you have to define, the CAD model. Right? So you either import a CAD model or you create a CAD model. You need some kind of geometry as a starting point for it. So some kind of geometry that you created in SolidWorks, or maybe you created it within ANSYS itself. That is the domain. Okay. So for our purposes, just so that you can have a visualization, I'm going to draw a domain. The domain is going to look just like an arbitrary potato. So that is our domain, or at least the abstraction, some abstract art of an engineering domain, okay? And so usually our domain, we break it up into two regions, right? So the interior of the domain, we usually specify that with a symbol omega. So think of kind of like the fleshy kind of white parts of the potato that are kind of on the inside. Okay. And then the other region of the domain is the boundary, or the thing that encompasses the domain, which we give that the symbol usually delta omega. So that's like the skin of the potato. You guys have the downside of being the last class I have to teach before dinner. And so you're going to see a lot of food-based examples because I'm thinking about what I want to do. Getting in and out with my buddies today. So I'm thinking about French fries, I'm thinking about double doubles and
Full team style.
no, full give me the carbs. Give me the bread. Okay, so the defining domain, kind of seems like an obvious thing. When you're working with, especially after you work with ANSYS for a while, it's kind of the first thing you do. Sometimes you don't really think about it when you get to FEA, but it's important, and it's important to define the domain, and for us to, most important to kind of get these labels, that omega, delta omega. So it's always kind of the first. The other thing that's not so trivial with the domain is, thinking about, what actually do I want to model? What do I actually want to include in my FEA simulation? That's actually a really important question to ask because, remember the goals of an FEA analysis, right? Usually when you're performing FEA analysis, you want to find out, or you want to perform, or you want to predict the behavior of a certain region in your system. So the most common case that we're gonna go, that we're gonna do in this class is we're gonna do failure analysis. So basically, we're gonna be, simulating the structure of a certain, part. We're gonna expose it to certain constraints, certain forces, and we want to see if the part's going to break or not. Okay, that's pretty common. If you're designing the structural parts of any kind of device or any kind of vehicle, that's kind of what you're interested in. Okay. But if you've ever designed something or if you've ever kind of seen something break, things usually break in the same places usually. And so if you place a lot of stress on something, it's going to break at certain points. So with that in mind, if you're really interested in just the parts that are going to break, maybe you just want to simulate those parts and not all the other parts. I'll never forget this, and this occurred a few years ago, so I could talk about it. But for someone's final project in this class, they wanted to do a finite element analysis of a barbell in a weight room, basically. And he was interested in seeing, how much weight can I put on this barbell before it kind of collapses on itself. And so, he worked really hard on this. And he basically created a SolidWorks model of his entire weight room setup. So the bench, the barbell, the weights, and all that stuff. And I'm like, this is beautiful. It looks great. We're only interested in the barbell. So all the other stuff that you're modeling, it's great. It looks beautiful, but we're only going to do finite element analysis on just the barbell itself. Okay. So you can try to do simulations on everything else. It's just going to be a very boring simulation. And so if you were to do a simulation on the bench, for instance, the bench really isn't going to be doing much because it really only has the weight of itself that needs to support, right? And so you want to be kind of really deliberate and really thoughtful about kind of what you include in your domain. And maybe it's better to kind of just include a certain portion of it where that's where most of the action is going to take place, where most of the stress is going to be. Okay. There are also considerations of utilizing things like symmetry, right? So symmetry is a very powerful tool that we're going to talk about kind of later in the class, where symmetry is able to kind of cut your domain in half. And that's pretty significant because if you cut your domain in half, that's half of the processing power that you need. Or maybe you can take all the elements that you were going to use for the full simulation and devote it to just that half. Okay. So being very thoughtful about your domain and kind of allocating your resources effectively was one of the really important skills for doing FEA. Okay. So even though for this class it's going to seem very simple, you're just going to take a CAD and just throw it into ANSYS. A lot of times, you need to be a bit more careful and thoughtful. And that's especially true for your final projects. And so, for your final projects, I know a lot of you are going to be using FEA for your senior design. Part of your senior design is you're going to create this beautiful CAD model for your senior design project. But, most likely you're not going to use all of it for FEA. And so, you may have to just do a sub region of it or do some kind of sub model, something like that. Okay. All right. Any questions on this so far? All right, so the next part of boundary value problem is the governing equations. So we've already kind of talked about the governing equations quite a bit today, but the governing equations are the differential equations that predict kind of the behavior of the system. And when I say behavior, what I really mean is we want the differential equation is going to tell us how our physical system is going to respond or react when external stimuli are applied to it. And so included in the differential, in the governing equations are also things like the material properties as well, okay? They affect kind of the solution. I apologize. It looks like I'm looking at my phone and I'm texting my wife, but I'm not. I didn't bring the lecture notes today because I thought we were doing the answers, so I have the notes on Dropbox and I'm like reading it like Senor Chang like this. I can't trying to read the notes and trying to communicate it to you guys. So okay. So we already talked about the governing equations a lot, so I'm not going to say too much more on that. Let's move on to the third part of a boundary value problem, which are the boundary conditions. So we mentioned boundary conditions a little bit on Tuesday. They're an important part that you have to apply in ANSYS as well, which again would have been great if we could use ANSYS today, but we can't, so use your imagination a little bit. But the boundary conditions are basically any kind of external forces or external stimuli that are going to have a direct impact on your system. So some of the more common boundary conditions that we're going to be working with in this class are things like forces. Things like constraints, and so places where our geometry is going to be fixed, that's not going to move. Sometimes the constraints are often called supports. So fixed constraints, fixed supports, same kind of deal. Basically, anything that we're not explicitly physically modeling in the domain, but is going to exert some kind of influence on our system. Okay. So those are the three parts of the boundary value problem. We have our domain, we have our governing equations that define how our domain is going to respond to certain stimuli, and then we have the boundary conditions, which are those stimuli themselves. Okay, and so to kind of visualize this whole process, we can kind of draw a figure. So let's say that we start with an arbitrary potato. Okay. And I'm going to go kind of with the kind of the example of structural mechanics. So you'll see this physical potato kind of deform. And so our potato here is our domain, right? We have an omega branded potato. Of course, our potato has our governing equations that are going to define how the interior responds. And then to this potato, we're going to have some external forces. So those external forces are going to be like boundary conditions. So let's say that we have a boundary condition like this. Maybe we have a fixed support here. Our potato is fixed to the wall, or it's impacting a wall right there. Okay, so this is another boundary condition. So this is kind of what your simulation setup would look like. So you would have your original domain. At this point, it would be discretized, it would be meshed, then you would apply boundary conditions. And then when you run the simulation, by running the simulation, we're going to get a prediction of how this physical domain is going to respond to that external stimulus. So let's say we ran the simulation, and so let's say that we got kind of a result that kind of looks like this. So this is our deformed domain, as opposed to kind of our undeformed. Okay. All right, so on the left, you can kind of see the setup for the boundary value problem. So, that's everything that we had to define. So we define our domain, we define our governing equations, our boundary conditions. These are all things that you're going to input into ANSYS as inputs, okay? And then after you run the simulation in ANSYS, what you're going to see as a result is on the right, which is the response. If I were to describe this with words, one way to think of a boundary value problem or an FEA problem is, we're going to define a physical system with, that behaves according to its governing equations. We're going to apply some external stimulus, and we want to see how the system is going to respond to that stimulus. So a little long-winded, but that's kind of one sentence that kind of summarizes the whole idea of a boundary value problem and kind of the mindset that you have for finite element simulations as well. Okay. So with finite elements, we have our system, often is defined by CAD model. It has governing equations depending on the type of material it's made out of, the type of structure it is, and we want to see what's going to happen when we apply forces to it. Okay. When you say it like that, it definitely sounds simpler, that it is, but it's always important to kind of keep all of these things in mind when you're defining an FEA. It really kind of helps kind of keep things focused. Okay, any questions on this? Okay. All right, so that's the basic idea with FEA, and ANSYS is kind of designed from the ground up to kind of follow the same process of defining your domain, defining your equations, you define the boundary conditions, and then when you run the simulation, you kind of predict what's going to happen. Okay, so the next thing I want to talk about are the types of equations or the types of physics that you can solve in FEA, or the most common ones. Right, so I'd say these are kind of the three most common categories, but there's some variations in these as well. Okay. So the number one type of equation that we're going to solve, this is the one we're going to see the most common in this class. It's called linear elasticity. So linear elasticity, it's a structural type equation, so you're gonna be inputting things like forces and pressures and fixed constraints, okay? And you're gonna be solving for things like deformations and structural stresses, okay? So linear elasticity is an equation that determines how objects deform in response to physical forces. So the mathematical form of this differential equation is basically just a generalization of Newton's second law. Okay. And so it looks something like this. So we have the divergence of the Cauchy stress is equal to, or excuse me, plus the force vector is equal to rho times partial squared u partial t squared. Where the main variable of interest here is u, where u here is the displacement of our physical system. So that's the differential equation essentially that we're solving with elasticity. So the main interesting thing about linear elasticity is the form of the Cauchy stress or the sigma term. Okay? So under linear elasticity, we're saying that there is what we're assuming is that there is a linear relationship between the stress in the system and the strain. And so this is probably a formula that you should hopefully be very familiar with, which is sigma stress is equal to Young's modulus E multiplied by epsilon, which is the strain. So in other words, that's our kind of familiar Hooke's law. So Hooke's law states that this relationship is linear. Okay, and the coefficient of proportionality here, or the linear coefficient, is E, which is the Young's modulus. So linear elasticity, I think, is probably the simplest structural equation that you can solve for. It's also the most intuitive. And again, this would have been great if we could do our ANSYS activity. But generally speaking, with linear elasticity, there is a linear relationship between the amount of force that you apply and the amount of deformation or displacement that you get. Okay. And so if you have a certain simulation that you're running under linear elasticity, and you've applied a certain amount of load, okay. If you were to double that load, generally what you expect with linear elasticity is that the amount of deformation should also double, right? So double the load, double the deformation. So a very strictly linear relationship. Okay. Of course, linear elasticity does have its limitations. Okay. So generally speaking, linear elasticity is only valid for relatively small displacements. And so if the amount of force that you're applying onto the system isn't that high magnitude, and the displacements that you're getting is maybe maybe 1 to 5%, maybe probably less than that of the total dimension of the structure, linear elasticity is pretty reliable here. Because if you think of the typical stress strain curve, so on the vertical axis here, we have stress. On the horizontal axis here, we have strain. Okay. So hopefully, you guys remember this from solid mechanics, right? But typically these curves look something like this, where there is an initial region that is a straight line that's valid for relatively small strains. But then after a certain point, this curve is going to start to deviate from that linear relationship. It's going to start to look something like that. Okay. So remember, this region of the stress strain curve, this is called plastic deformation. Okay. And so it's when deformation or the strain really starts to take off, you get a lot more deformation for the amount of stress that you apply. Okay. So linear elasticity basically makes the assumption that you're kind of just staying in this region right here. Okay. One other thing that I'll mention before we move on to talk about the thermal equations is the primary solution here. Okay. So I kind of hinted at it a little bit when we looked at the equation up here, right? But every differential equation has what I call its primary variable, or the first thing that it solves, right? It's a little bit hard to tell when you're just using ANSYS what the primary variable is, because ANSYS kind of treats all the outputs as kind of the same. But when you're solving a differential equation, there's always a primary variable that you solve for first, and then from that primary variable you can compute a bunch of other things. Okay, so for linear elasticity and for structural simulations in general, the primary variable is the displacement, or sometimes we call it the deformations. So in the computer, this is the first thing that it solves for first. If you're solving a static structural simulation, the first thing ANSYS is going to solve for is the displacement, right? You have your physical system, you apply constraints, you apply loads. First thing it needs to solve for is how much is the structure going to displace and deform in response to those loads, okay? And then from the primary variable, from the primary solution, ANSYS is then able to compute what are called derived variables or derived solutions. So some common derived variables for structural simulations will be things like structural stress. Strain is kind of in this boat as well. Under that token, ANSYS actually also lets you compute things like factor of safety. for more specialized simulations, if you're doing, columns or something like that, you can compute buckling, stuff like that, okay? But the first thing that's solved for first is always the displacement. So this is an important distinction to know when you're working with FEA, because in general, when you're talking about accuracy and reliability, usually your primary variable is going to have the highest accuracy, right? And what I mean by that is that when you solve a structural simulation for displacement, you can tell what you can probably have the most confidence that your displacement is the most correct. Okay. And then because the derived variables are computed from the primary one, these generally have lower accuracy than. Later on in the class, we're going to talk about a concept known as mesh convergence tests. And so, what we'll see, throughout the class is that, the accuracy or the reliability of your simulation depends very heavily on the mesh density, or how many elements that you have. And what you'll see is that the primary variables in your simulations, the displacements, the temperatures, for fluids, it's velocity. The primary variables are always going to converge first. And so, you'll get a reliable solution for a lower amount of elements for the primary variables. Whereas the derived variables, they're going to converge a lot more slowly. So that's definitely something to keep in mind if you're running your simulation for a derived variable. Most of the time most of the time, we're interested in like stresses and a factor of safety. You want to make sure that you're really careful with your mesh convergence. Okay. All right. Any questions on that? Okay. So that's the structural equation. So I wanted to spend the most time on that just because we're going to be doing this a lot in this class. Another very common type of equation that's solved in FEA is thermal equations or heat transfer. We won't do too much in the class with heat transfer, although I know a lot of you have interest in doing it for your final projects, and so we'll kind of cover it near the end of class. But heat transfer, technically speaking, heat transfer is actually an easier equation to solve than structures. And so if you're learning FEA from kind of a theoretical point of view, the heat equation is probably the first equation that you're going to solve before Navier-Stokes. Well, Navier-Stokes is really crazy before the structural. So heat transfer, you guys have all taken heat transfer, so there's not much to say. But in thermal simulations, what we're interested in is solving for usually the temperature distribution within a physical domain. And usually, we're interested in this because we're subjecting our domain to some kind of thermal load. So usually this means some kind of, maybe external heaters or maybe external cooling. Maybe it's attached to something with a fixed temperature, and we're interested in seeing, how this is going to affect the temperature throughout the model. Okay. Sometimes this also includes things like friction. So last year, I think someone did a project of the braking system in I think it was either Formula or Baja, and then they applied a thermal boundary condition based on the amount of friction, how much heat that's going to generate as the car kind of comes to a stop. Okay. Okay, so the governing equation for heat transfer is, of course, the heat equation. I love the heat equation because it's one of the very few equations in science that's not named after some dude. Right, so for some reason, scientists are very narcissist people, they name their equations after themselves, Bernoulli equation, Navier-Stokes equation. Reynolds number, it's great, they're immortalized, but if you tell a stranger, what the Navier-Stokes equation is, they would have no idea. But if you tell someone I'm solving the heat equation, it's clear what you're solving for heat. So I love the heat equation, unless this person's name was actually Heat, I don't know. Maybe he is a narcissist, but at the very least, at least on first blush, it looks nice. Okay. So I'm not gonna write down the heat equation, you guys have seen it probably already in 407, but I will make note of the primary variable. So the primary variable in thermal simulations is temperature. So when you solve a thermal simulation, temperature is the first thing that's going to solve for. Okay. So some common derived variables. Some common derived variables that are solved in thermal simulations are things like heat flux. That's probably the most common one. And so you want to find kind of the direction and the amount of kind of energy lost usually in a certain direction, or maybe energy input. Okay. Kind of everything is kind of a derivative of heat flux. And so things like energy loss, yeah, things like that. Heat flux is probably the most common derivative. All right, so that's heat transfer. The third one that I'll go over, just because these are probably the three most common for mechanical engineers, is fluid flow. And so the fluid flow equations, these are going to solve for, the velocity distribution of fluid kind of flowing through a certain domain. And usually, you need some kind of driving force that's going to drive this fluid forward. So the most common, external force or boundary condition for fluid flow is some kind of pressure. And I'll say usually, but sometimes gravity plays a role, but usually it's driven by pressure. So of course, the governing equations for fluid flow is the Navier-Stokes equations. The Navier-Stokes equations represents the conservation of mass and momentum in a fluid. The primary variable for fluid equations is velocity. And some derived variables. So these I'm quite familiar with because all my past research has been in CFD, so I've seen these before. So these could be things like pressure, Sometimes you're interested in shear stresses. Because as fluid kind of flows past each other or flows past a solid object, it's going to invert some frictional shear. Okay. Maybe things like vorticity if you're into aerospace. Okay. Drag forces, lift forces, all kind of included these. All right. So those are the three most common equations that we'll solve on FEA. Of course, FEA is not limited to these three things, and so FEA is able to solve for basically anything that's governed by a differential equation. But these are the three you're going to see the most as a mechanical machine. Any questions on this? Okay. One last thought that I want to leave you with before we head out for today is the idea of a multi-physics simulation. So, in kind of the traditional way, and ANSYS is kind of set up this way too. The way ANSYS is kind of set up is that you kind of choose one kind of equation. So you're either going to do a structural equation or a thermal equation or a fluid equation. And you're solving for just that type of equation. So those are called single physics type simulations. But in reality, these different equations, these different types of phenomenon, they're going to interact with each other and affect each other's solutions. Okay. And so oftentimes, you don't have strictly just a structural situation, or you don't have strictly just a fluid type situation. Oftentimes you have multiple things happening at once. And that kind of necessitates you, in order to get an accurate solution, to solve multiple phenomena at once. Okay. And so let's look at a few different combinations and see what they look like, and kind of talk a bit about how they affect each other's solutions. Okay. So the one I'm most familiar with is the interaction between fluids and structures. And so these are called fluid structure interaction simulations. FSI. I'll give you one example from my research. So my research, a lot of what I research has to do with simulating blood flow, right? So simulating the flow of blood through a person's body. Blood will flow through your blood vessels, which are flexible structures. So we can think of a situation of blood flow, or it doesn't have to be blood. So maybe a fluid flow through a flexible tube. Okay. We have a tube here, we have fluid flowing through it. And we have some kind of internal pressure, we'll consider the pressure drop from the inlet to the outlet, P1, P2. Okay. So that pressure difference, P1, P2, that's needed to drive the fluid forward. But that pressure is also going to exert a force on the vessel wall. Okay? So that pressure is going to exert, a force that kind of radiates outward on the wall. And so the wall, being kind of a flexible, elastic structure, is going to respond to that. Okay? And so as blood kind of pumps through this this tube, the tube here is going to expand. Okay? And so there you kind of have the interaction of a fluid force kind of influencing and causing a structural deformation. Okay. But it also goes the other way around too, because what happens when you have a flexible tube or a tube filled with fluid and you suddenly kind of pull it apart and expand it, you're going to create a vacuum, right? And so as the tube kind of expands, it also kind of has to pull. Let me change the color as you can see. It's also going to pull some fluid towards it, right? So the structure expands, it pulls some fluid, and that's going to affect fluid flow. And so what affects the fluid flow is going to affect the solid, right? And so what you have here is a true kind of multi-physics situation where you can't just solve the fluids. If you solve just the fluid domain, you're going to miss out on all of the structural mechanics. And of course, you can't just solve the structural mechanics, you're going to miss out on the fluids. These two systems or these two types of physics are very closely intertwined. And they need to be solved simultaneously in your simulation if you want to apply. Okay. So ANSYS does have the ability to do multi-physics. Some people have done it for their final project, but that's just kind of something to keep in mind. Any questions on this? Okay, one more example. So I did kind of mention this one earlier. So this is a thermal structure interaction. So let's look at a brake pad, right? So when you brake on your car, you have your brake pads that kind of pinch the axle, and that causes eventually the wheels to stop with friction. We have your kind of spinning axle here, and then you have kind of a brake pad that kind of pinches it, maybe something like this. So normally this axle is spinning, this disc is spinning really fast. And then to slow it down, you pinch it at a certain point, and then that friction force is going to cause it to stop. Okay. But because we're stopping this primarily through friction, it's going to produce a lot of heat. And of course, that heat is going to heat up the axle, and it's going to heat up the brake pads. Okay. So this entire system here is going to heat up as the axle kind of comes to a stop. Okay. And what's fascinating about this is that, and this is fascinating for any kind of thermal simulation, is that often the material properties of the system depend on temperature, right? So as the entire system kind of heats up, that's going to change its properties. And so it's going to change the values of the Young's modulus. It's going to change the value of the density. It's going to change the value of the Poisson's ratio. And so as the material gets softer, as the material properties kind of drop, that's going to affect its structural response, right? So maybe if you pinch it too hard and it gets so hot, then the whole thing kind of just gets bent out of shape. Okay. So this is another situation where you have the structural component and you have the thermal component, and they're very kind of closely intertwined with each other. And you need to solve both at the same time in order to get kind of the full picture of kind of what's going on. Okay. So multi-physics situations, we're, it's possible, you can do them. For our activities, we're gonna kind of shy away from them, but I just want to let you know that they are possible, and you can set them up in. Right, any questions on this? Okay, so that's all for today. I apologize if it was a little bit unorganized, I was trying to read my notes on my phone. But I'm gonna contact IT today and hopefully get answers ready for Tuesday. So Tuesday, hopefully answers activity once the issue with the mic and server is sorted out. So thank you guys for coming today. I apologize we couldn't do answers. Hope you guys have a good long weekend and I will see you on Tuesday.
All right.
I just like, let's get more. You know what we should do.
I see
It's scout.
Yes, there's one there.
Sold out.
Okay, yeah.
It's just since we first. Yeah, by any chance there's so. Maybe since we only. Do analysis of.
I finally had to do like.
Yeah, no, you definitely can use answers for biomechanics.
Oh.
The difficult thing is that for tissue, like bones and muscles, that they are materials. And so we talked about today linear elasticity, you can't really use linear elasticity.
But if you skip them all and they give you a makeup and
Some like hospital, they actually use titanium for like broken feet.
Hmm.
And then they 3D printed like in their place.
Oh, wow.
And then they actually, so I don't know if it's like elastic. But if that possible, like is access able to like do.
Yeah,
Like
yeah.
roads and everything.
Oh, yeah, definitely.
For sure. That's the thing.
Yeah, yep. Hey guys. Yeah.
Ooh, what nice you got taken.
Oh, yeah, so I've been receiving a lot of mail, so I think I responded to, quickly, but yeah, I'm working through everything else. So I got it, but I registered it, but then I'm like, I got 20 others to get to, so. Yeah, that's. Oh, okay, so I think I added you to the Canvas site, so I need to add both of you to the Canvas site too. Yeah, so let me do that when I get back.
Okay.
And then can you send me an email too, if you haven't already? Or you said, okay, I will make sure. Yeah. Yeah, thank you guys, have a good day.
Hi.